Okay, if you're at this video, then you've been doing a good job, or else you just decide to skip the other three and see if you can make any sense. We're going to try to make some sense with this final video on p-value. It basically answers the question, how do you know your stats are significant? When you find a mean of something, like the BMI of the women that we were talking about in a previous video, how do you know that that number is actually significant? And so a p-value gives you the probability, and it really gives you a support for the claims that you can make with your statistics. So we're going to look at that in this section here. So here's the slide for this p-value. It's in your book as well. We assume the null hypothesis is true. That's what we've always been saying. The probability that the test statistics would take a value is extreme or more extreme. Then the value actually observed is called the p-value. Now remember, we sort of did this in the last video with the bank and the bank, the statistics on the insurance and on the grocery store. So the smaller the p-value, the stronger the evidence the data provided against. So in other words, the smaller the probability that you made a mistake, then you've got really strong support against the null hypothesis. In other words, you're trying to find if there's a difference. So if you have a small p-value, if you can say like 0.005% that I'm wrong, then you have a pretty strong case. So a small p-value indicates a small likelihood of observing the sample results were just at random were true. Okay, so that's what that means. So here is what we did in the other video. Here's our alternative hypothesis. If we want to have, we find the mu is bigger than the mu of the null hypothesis, so the p-value is the probability, again, the value is larger than the observed test statistic z value. Okay, so we want to see if it's really significant. So in other words, if I mentioned in a previous video, if using these techniques of videos and LiveScribe will make you a better student, then I can compare this class to the previous class, but I want to see if the numbers, if I was able to get some data out of that, rather than just test grades, but some type of data, how much you respond on Blackboard and so on, then are the numbers that you provide me really significantly different than the ones from the previous class? So is my idea that the videos are making a difference really significant? I can't say that yet, all right? And the same thing goes if you do the second one here, which is alternative, the mu is less than the null mu. Okay, so the mu that you find, p-value is the probability, again the value is smaller than the observed statistical value. And then this is when you have two-tail, remember the two-tail system here, so we have mu is not equal to the mu of the null hypothesis. So those were the three that we looked at in the previous video. Okay, so we go back to the sweetening colas here, case study 1. Now this test statistic, the z was 3.23. Is that really significant? And alternative hypothesis was that H alternative mu is less than 0. The p-value would be, is the p-value of that. You take 1, and with the 3.23, how do we get that? We find the z value of the 3.23. All right? We find that, we subtract it from 1, because that's the percentage, you get 0.0006. So if the null hypothesis is true, there is only a 0.06% chance that we would see results at least as extreme as those in the sample. Thus, since we saw results that are unlikely if HO is true, we therefore have evidence against HO and in favor of the alternative hypothesis. Okay, and this is what it looks like. Our p-value for z of 3.23 is way the heck over here. Okay, it's way here, and looks how far. So we're saying it's significant. That's one standard deviation, by the way. So that, if you do the probability, you get 0.0006, which you change to percentage, you get 0.06%. So that tells you that this number is really significantly different than the mean. Okay, if it would have been over here, it wouldn't have been so significantly different. Case 2, studying job satisfaction. Suppose job satisfaction scores follow a normal distribution with standard deviation of sigma equals 60. We data from 18 workers, gave a sample mean score of 17. If the null hypothesis of no average difference in job satisfaction is true, the test statistics would be, now this should be familiar, this equation, it looks just like this one over here. Okay, found the z over here. So this z is found, we get 0.120. What's it look like? 0.120. So for test statistics, z equals 1.20, and the alternative hypothesis mean that there's no difference. the p-value would be, here we go, 1.20. Let me figure it out. And we did, since this is both sides here, two probabilities, it's both tests, it's both sides, we get a 0.2302. So if our hypothesis is true, there is a 23, that's pretty high, chance that we would see results at least as extreme as those in the sample. Thus, since we saw results that are likely if HO is true, we therefore do not have good evidence against HO and in favor of HI. So there is no significant difference here. Okay? So this is what it looks like. The two-sided p-value for z equals 1.20. 1.2. You put 1.2 from 0 from the mean, both sides, negative 1.2 and 1.2. Okay, and you find the z value here, and you'll get an area of 0.1151 and an area of 0.1151 there. So see, it's not significant. It's not a significant difference here. So if the p-values are small or smaller than the significant level, the one that you set, then we say that the data give results that are statistically significant at level A, alpha. If we choose alpha as 0.05, then we are requiring that the data give evidence against HO so strong that it would occur no more than 5% of the time. Okay, and if we choose alpha as 0.01, we are insisting on strong evidence against HO. So that's 90. So evidence is so strong that it will occur only 1% of the time. Okay, so that's when HO is true. So if you're going to be doing a test like this, let's say you're really ambitious and you have the understanding and you want to do this for your research paper, which you really have to get going here. So the 4 steps in carrying out a significance test is state the null and alternative hypothesis. My new way of teaching stats is not any different from the old way of teaching stats. That's my null hypothesis. The alternative would be that there is a difference. Therefore, that there is, I would just put does not equal a 0. Okay? So I calculate the test statistic, right? And I find the p-value and I state my conclusion, whether it's significant or not. Okay? And that's what basically is. So the z-test for a population mean, this is what it looks like here. You draw an SRS of size n from a normal. I'm going to put this in slide format so you can see it much bigger. Okay, draw an SRS of size n from a normal population that has unknown mean mu and known standard deviation sigma. We've been saying that all these 4 videos. To test the null hypothesis, that mu is a specified value. Here. Boom, 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 boom. We say it's equal. There's no difference. Calculate the one sample z statistic. Okay? That's what you do next. Is that equation. In terms of a variable z having the standard normal distribution. Okay? You put it there. Okay? The p-value for a test of HO. So if you set a p-value at 0.1, at 0.01 or 0.05 or 0.1, you have to decide that before. Okay? And where does that number land? And that's what it tells you. Okay? So, and escape again. So the sweetening cola is here. Here's the hypothesis. It's going to be higher. That's what we're hoping to find. Test statistic, we found it. 3.23. Okay, so you find that. So we set a the 0.01 format here, and then we find the p-value. It says right there, p of the z minus 3.23. Okay, the z-score, that's what we set. The probability that it's going to be this is 6%, it's 0.06. Since the p-value is smaller than 0.01, okay, that's what our alpha was set, 0.01, there is a very strong evidence that the new cola loses sweetness. And then the last thing, case study 2, the hypothesis was equal or not equal. Here's the test statistic, 1.20. And this was a 2-tailed test, so that's why we have 2 on both sides, okay? And this p-value is larger than 0.10, okay? There is not sufficient evidence that there is any change. And we can look at that in the book here. And you can also look at your applet here. Like looking at this problem, job satisfaction from 18 workers. What's it look like? Here are the numbers, and this is what it looks like. So we have a p-value in the shaded area. The z-score was 0.2302. Okay, so here's the main point, and we go over here and we figure out what this value x is going to be. All right, and the observed value of x is 17. Okay, and that means that it's not good evidence against, therefore, right here. Values as far from 0 as the 17 would happen 23% of the time. Okay, that means that's not very good stats. You want it to be very small. So that means that you can't reject your number. You can't reject, I'm sorry, you can't reject your null hypothesis. If you go to the applet, you can do some experiments, and I would urge you to do that. It's to try different ways of doing it. So you set an equal to 0, or you can set a one tail. So here's your null hypothesis, mu equals 0. Here's your alternative hypothesis. So you do, and then you do 10, and you do an update over here, and you can find out. Okay, I have data and the record is 0. Show P. Okay, you can generate a sample. Okay, there's a sample there. Reset it. Let's try more. Okay, so we update 20. We have 20 people. Generate a sample. Okay, we found our X bar over here, and you have to make the decision. So I would urge you to look at this applet, which can be found on the same page that when you sign up for the quizzes. And that is it. If you have any questions, don't hesitate to ask me. And take your time with this chapter, as I've said before.